Hello and welcome. Here we're going to take a look at our 8586 quiz. For number one, we want to rationalize the denominator. One thing I noticed with that one though right away is that the numerator, the 121, is a perfect square. So if I split that up, I can get 11 over the square root of 3. So that makes that kind of nice to handle. And then in order to rationalize the denominator, we multiply by the square root of 3 over the square root of 3. And so we get 11 square roots of 3 over 3 as the result. Moving on to number 2, again rationalizing that denominator. And you could simplify some stuff here, but because it doesn't work out perfectly, I might just wait to do that. So looking at this one, I have a y to the 5th in the denominator, so what I would choose to do there would be to multiply by a square root of y. The reason for that is because by doing that, I end up with a square root of y to the 6th in the denominator, and that's something that I can square root perfectly. I just get y cubed. So building that y up 1 is why we make that decision. Now we still have to then deal with the numerator, 45x cubed y, and then we can split that up and simplify that as well. So the 45 would split up as, let's see, a 9 and a 5. The x cubed we could split as an x squared and an x, and there's not enough y's there to square root any. So we end up with our square root of 9x squared is 3x. We have that square root of 5xy, and we've got that y cubed there. So that's what we're looking at for number 2. Number 3, simplifying this, so really we have to rationalize the denominator. Now notice we have a cube root here, not a square root. So we have that 7 in the denominator. I'm just going to rewrite this here. And so what I need to do is multiply that by something that will make that into a perfect cube. In this case, I have to multiply by 49, which of course is the same as 7 squared. So again, 7 squared and 49. I'm just going to write it in both ways so we can see both of those. So I would have to figure out 4 times 49. So I get the cube root of 196. And the 7 times 7 squared would be 343. Now we do that intentionally because 343 is, of course, a perfect cube. We get 7. And notice with the 7, that's a prime number, so it doesn't have any repeated factors. And we could look at trying to break down the cube root of 196, but I can see its factors. It comes from a 4 and a 49, so it really has a couple of 2's and a couple of 7's, but not 3 of anything. So the cube root of 196 does not reduce. Looking at number 4, same sort of idea. We want to simplify that cube root. We do have the negative that's out in front. It really isn't going to do much. Just make sure you don't forget that is there at the end. Since we have a plain y in the denominator, we'd have to multiply numerator and denominator by a y squared. And again, I'm really multiplying by a cube root of y squared to both the top and bottom, which ends up being the same thing. It's just kind of sneaking the y squareds under the radical. So the numerator, I get a cube root of 3xy squared, and then in the denominator I get a cube root of y cubed, and so I end up with a y in the denominator and a cube root of 3xy squared in the numerator. And so that's what that turns out to be for number 4. Number 5, we have binomial in the denominator, a 9 minus the square root of 2, so I have to use the conjugate for that, which would be 9 plus the square root of 2. In this case, at least it's not too bad for figuring out the product of my numerator, since it's just a 7 there. We just distribute the 7 through, we get 63 plus 7 square roots of 2. You can box or FOIL out this denominator. However, with these conjugates, there is a special pattern where it ends up just being the first term squared. Maybe I'll even just write this down. So a plus b times a minus b is a squared minus b squared. Now it gets to be a little interesting when we have things like square roots in there, or even like, you know, a 3 square root of a 2 could be interesting. But again, you can still kind of use that to figure that out. So we get a minus 2, and again, that's from squaring that square root of 2. Just ends up being a regular 2. So we end up having our numerator stays the same because we can't simplify that at all. 81 minus 2 just gives us 79. Alright, so number 6. Now this is just kind of an interesting combination because the numerator is the conjugate for the denominator. So we end up multiplying numerator and denominator by 10 minus the square root of 3. And again, it just happens to be the case where the numerator is the conjugate of the denominator. So we have to multiply those together. Now, again, different ways that you can do that. I think for the denominator here, again, I'll just use the pattern. So I square the 10, I get 100, and then minus, and I square the square root of 3, which is just 3. So I'll end up with a denominator of 97. Now the numerator gets to be a little bit more complicated. So I'm going to go ahead and draw a box for that. So we get 10 minus the square root of 3 on the left and 10 minus the square root of 3 on the top. So we get 100, negative 10 square roots of 3, another negative 10 square roots of 3, and here we get the negatives to cancel out, get the square root of 9, which is just 3. So grand total, we get 103 minus 20 square roots of 3. So really that's what goes over our 97. So just extend that a little bit. So 103 minus 20 square roots of 3. Of course, we'd want to reduce that if we could, but it doesn't reduce at all, so we just leave it like that. So again, there's our final answer for that one. Let's see, so we just want to write this in lowest terms. We don't actually have a radical in the denominator, so we don't have to rationalize, but we can reduce that square root of 56z cubed. So we'd have that 14z. We'd split this up into what we can square root and what we can't. So 56, let's see, how would we split that one up? So really the largest perfect square factor that goes into 56 is 4. And again, if you need to create the list of those factors for 56, because you can't just kind of figure that out, that's fine. We would take a z squared out of the z cubed, and so that leaves us with a plain z in the other radical. And again, this is my 2, it just kind of looks z-like. Let's see, and then the denominator is just the 7z. Well, again, kind of thinking ahead, we can see how this will end up reducing because we'll have a 2z here and a square root of 14z there. And it's all over the 7z. The numerator has a common factor of z, so we could factor that z out. We'll leave in a 2z, but the 2 isn't going to cancel, so we could just leave the 2 in there. So we get 14 plus 2 square roots of 14 z over the 7z. So the z's will cancel out, and we get the 14 plus the 2 square roots of 14z all over 7. And again, that's all we can do as far as reducing that down, so we leave it like that. So solving equations. Again, first thing we want to do here with number 8 would be to isolate the radical, so we would add 10 to both sides. So we get the square root of 3x minus 10 equals 10. And we would square both sides to get rid of that square root. So we end up with 3x minus 10 equals 100. We would add the 10, we get 3x equals 110. And then we divide by 3 to see what that would be. And doesn't reduce at all. I guess I'm perfectly fine with just leaving the answer as x equals 110 over 3. If you prefer to think of that as a decimal, it's 36.6 repeating. And again, extraneous solution is not really possible there because when we squared both sides, we can't have squared a negative. For number 9, we will have to consider extraneous solutions. We would start by subtracting 5, and then we would square both sides. And again, the issue becomes here that when we square x minus 5 is negative for certain values of x. So we have to be aware of what we're doing there. And again, you could box or FOIL the x minus 5 squared, but we get x squared minus 10x plus 25. And then we want to get everything on the same side, so we subtract the x and the 7 in order to simplify that. So we get 0 equals x squared minus 11x plus 18. And we'd like to try to factor that. Looks like it'll factor as x minus 9, x minus 2 would give us what we need. So the solutions appear to be 9 and 2. And I say appear to be because remember when we squared that x minus 5, I mentioned we run into trouble if x minus 5 is negative. Well, x minus 5 is negative if x is 2, because 2 minus 5 would be negative 3. So the 2 would be an extraneous solution. Now when x is 9, that's fine because then 9 minus 5 is 4, and so the 9 works out just fine for that. And then looking at problem 10, we would subtract the 9 from both sides. Now, again, I can tell right here that when I take both sides to the 4th power, I just created an extraneous solution because I took a negative to a 4th power. So this would have no solution. You could go through the process and figure out what the answer is, plug it back into the original, and it will not work. Number 11, we'd want to isolate one of those radicals. I'd probably leave the 2 minus x where it is and do the 4 minus the square root of x plus 6. So we square both sides. In the left side, pretty simple there. The right side, we have to do a little bit more work to figure that out. So I'm going to move down here. And I would set up a box for this because it's fairly complicated. And so we've got a 4 minus, and then a negative square root of x plus 6 here, and a 4 and a negative square root of x plus 6 there. And I just went ahead and filled in that product table, so we get our 16 and our x plus 6. So those can be combined, and they give us x plus 22. And then we get our negative 4 square roots of x plus 6, so 2 of those would make it minus 8 square roots of x plus 6. Now believe me, this problem does get to be a little bit messy. We want to then try to isolate this as much as possible, so we subtract the x and subtract the 22. So subtracting that 22, subtract the 22, subtract the x. So we actually end up with a negative 2x minus 20, and that will equal our negative 8 square roots of x plus 6. Again, really our goal here is to try to isolate this square root of x plus 6. So we're trying to isolate that square root of x plus 6, but we want to do that without creating fractions. So I wouldn't want to necessarily divide by the entire negative 8, but I could divide by a negative 2, and that will not make any fractions there that can't be simplified. So on the left side then we would end up with x plus 10, and on the right side we'd have 4 times the square root of x plus 6. So we have that radical isolated as much as we would want to at this point, so we go ahead and we square both sides. The one trick to that is that when we do have that 4 on the outside, we have to remember to square that. And then squaring the square root of x plus 6 just gets rid of the square root. And again, you could box or FOIL that x plus 10. We get x squared plus 20x plus 100 when we square that. We do need to distribute the 16 on the right side. So this will stay as it is for a minute here. We get 16x plus 96. It is quadratic, so we would want to move everything to the same side. So we'll subtract the 16x, subtract the 96. That makes the right side equal 0, and the left side becomes x squared plus 4x plus 4. Now this actually factors pretty nicely. It's even a perfect square trinomial. Factors as x plus 2 squared equals 0. So what that means is that we have just one solution, x equals negative 2. And in this case it probably is just simpler to look back at the original and make sure that negative 2 does make sense in that original question, which if you plug the negative 2 in, you get the square root of 4 plus the square root of 4 equals 2. So 2 plus 2 equals 2. So that answer of negative 2 does make sense there. Well, thanks for watching. Hopefully this was helpful, and if you have any questions, let me know, and be sure to work through your own version of this practice test, or practice quiz. Thanks again.